chapter 16, part B. This is on principal ideal domains. So this is introduced in the book in chapter 16 because the book has sort of tied their examples mostly to polynomial rings, but principal ideal domains don't have to be polynomial rings, so it's sort of better to list it separately, even though we're going to mix it up with polynomial rings a little bit. So a principal ideal domain really is nothing more than a special type of integral domain. So a principal ideal domain this will be abbreviated PID to keep it handy, is an integral domain R in which every ideal is principal. If you've forgotten what that means, that's meaning every ideal has the form ideal generated by A for some A in R. And if you've forgotten what that notation means, this means this is formally this is the principal ideal generated by A. This is the set of all RAs for R and R. So a principal ideal domain is an integral domain in which this always happens every single time. So the first theorem, this is sort of where the book starts to really connect this up to or focus on polynomial rings, that if capital F is a field, then Fx is a PID. So we have to prove a few things here. We have to prove that it's an integral domain in which every ideal is principal. Two things. So first of all, since F is a field, F itself is an integral domain, just a regular integral domain. This is because every field is an integral domain. So then, by a theorem in the first part of chapter 16, if you start with an integral domain and you adjoin X, you get an integral domain. So now we know that Fx is an integral domain. We need to show that every ideal is principal. So I'm going to pick an ideal. Let's say let I be an ideal in Fx. So one of two things is true. Either it just contains 0, the 0 element, or it doesn't. Right? So if it just contains 0, then we could say that it's generated by 0, and we're done. So if I is not 0, so what I'm going to do is I'm going to pick a polynomial, pick a non-zero polynomial in I that has minimal degree. Now this technically exists by well ordering, but we don't need to be formal. We could just sort of say, look at all the things that are in I, pick something that has the smallest possible degree that's not the 0 polynomial. Right, so I want to pick something else. Now, suppose g of x is constant. Right, so if a constant is in the ring, then the ring is everything. Right? So because specifically, if a constant is in there, then 1 is in there. Right? So in other words, let's be formal. Then say some alpha well, I'm using the word constant badly, something in f, some alpha in f is in I. But then 1, which is f times f inverse, is in I. And then everything's in I. In other words, it's just generated by 1. And we're done. So suppose g of x is not constant. So maybe it's linear or quadratic or something. So what I'm going to do is I'm going to claim that I is generated by g of x. Okay. Now, first of all, since g of x itself is in I, we know that the ideal generated by g of x is a subset of I. We just claim the reverse. So pick something else I. And by the division algorithm, I can write f of x is something, some quotient, times g of x plus r of x, with 0 less than or equal to the degree of r, which is less than the degree of g. But now look, if we solve for r, we get f of x minus q of x, g of x. Now, if you look at all these pieces, right, f is in I, g is in I, which means this product is in I, because it's an ideal, which means this entire thing is in I. But it has degree less than the degree of g, and that contradicts the fact that g was minimum. Let's say smaller degree, to be really, really clear, than g, a contradiction. Unless, of course, r is 0. Right, because we pick g to be a non-zero polynomial. Right? So then r is 0, so f of x is q of x, g of x. So f of x is in the ideal generated by g of x. That's sort of a type QED there at the end. So that proves that if you start with a field, you get a principal ideal domain when you construct the polynomial ring. Now, the other thing that gets established by this more than what we just said, which will be useful later on, is that it's not just that it's a PID, it's just that what we showed in all of this is the generator of it is a non-zero polynomial of minimum degree. Right? Like this was back here, we said let g of x be a non-zero polynomial in I with minimal degree. And we showed basically that I was that guy. Now that works even if g of x is a constant. It still works out because this thing we could have just written I is g of x here for that constant. I just sort of rewrote it as 1 just to be different. So in other words, we can write the following. So for a corollary, we can say the following. Let f be a field, and I a non-zero ideal. Then if g of x is in I, then I equals the ideal generated by g of x if and only if g of x is a non-zero polynomial of minimum degree in the ideal. So the proof of this is sort of built into the previous. In other words, the method in which we worked it out. So just as a closing note, if you don't start with a field, this may not be the case. So in other words, if R is not a field, then Rx may not be a PID. May not be a PID. So for example, in Z of x, the ideal, so I can still write an ideal as follows. The ideal x2, which is generated by x and 2, is not principal. In other words, there is no g of x in zx such that x2 is generated by single g of x. This may not be screamingly obvious. I will say try it. It's a fun question to try, so I encourage you to give it a go. It's not hard. Basically proceed by contradiction perhaps, or look at like what things in here, maybe here's sort of a hint to think about, is like look at what do things in here look like. And then why couldn't this do it? It's sort of a fairly fundamental problem to try out. So give it a go. That's the end of 16B. Nice and short.